let me give a broader introduction, not necessarily about Adam Drobot, but about this event. This is so-called Industry Spotlight. This is 11th episode, and it is sponsored by a corporately zoned program of Santa Clara Valley section and by Computer Society chapter of Santa Clara Valley section as well. And we usually hold it by the end of the month, last Tuesday or Wednesday, if there is conflict other than presidential speech. And it's my great honor and pleasure today to host Adam Drobot. Adam Drobot has a long history of leadership and technology positions. He was managing director and CTO of 2M companies, president of Applied Technology Solutions, CTO of Telcordia, and many other. At the moment, he is a chairman of Open Tech Works. And Adam Drobot will be talking about digital twins. So with no further ado, Adam Drobot.
Okay. So Dejan, thank you for inviting me to this. It's my pleasure to do the talk. And let me just start off by saying that I'm actually involved in a project to do a book on digital twins with Springer. And I see a few of my co-authors have actually signed on for this. So I'm going to start off by saying just a little bit about the book, because it's a comprehensive look at digital twins. It sort of looks at the rationale of why they're important, the business aspects, a lot on technology, and then a lot of application areas. And overall, I'd say it's something like 38 chapters at this point, okay? So quite a few of the things that I'll be talking about come from that. I have two conspirators in this, Roberto Minerva and Noel Crespi, who are both in Paris, France, a little bit too late in the night for them. And I thought of the following, you can go and do a very deep presentation, throw up a lot of equations. What I thought I would do for today is sort of a little bit of a travelogue through what the digital twin is about, why it's important, talk about the technologies that underlie it, a little bit about business models, and then what I'd like to do is actually jump into some applications. So I think the first thing I'd like to say, there are many places I could have started. I actually spent quite a few years building electromagnetic simulation codes of various kinds, trying to replicate natural phenomena, physics of various devices. But when it comes to experience with something like digital twins, I ended up with a few of my colleagues in SAIC who worked on something called the America's Cup. And in 1987, there was an issue about Stars and Stripes. It was the America's Cup boat, and it ended up actually winning the cup during that year. And it was, I would say, a pretty comprehensive display of what something like a digital twin could do for you, okay? So I take the few words that are up there. The winner of the America's Cup competition embodied the results of a concentrated technological effort in sailboat designs, and the article recognized that computers played a significant role in the victory. So what I'm going to do is start off with that story because it sort of motivated my journey of spending time on things that dealt with large systems design and the kind of tools that the digital twin represents. Okay. So, oops, going in the wrong direction. So I think what you'll see on this page is sort of what ends up being the sweet moment. It was actually the victory Dennis Conner on the left-hand side was the guy holding the America's Cup. And there you see it sailing in sort of fairly rough seas. This is off Fremantle, Australia. And then you also see a model of the America's Cup boat, the Stars and Stripes. And what is very unusual about it is it took a trick from the Australians, and it has a winged keel at the bottom of the boat, essentially. And it turns out that that keel is very, very important. So the team that built this, and I had was lucky to have two people in my group who had actually worked on this. Neil Salveson, who was a naval architect, Marty Fritz, who had a PhD in computer science from Yale, and did hydrodynamics for a living. What they did is during the campaign for Stars and Stripes, actually built 4 different models of the boat, totally instrumented. Those were sailed off Hawaii. Everybody compared to how they were doing, and then build a series of models that involved hydrodynamics, aerodynamics, structures of the boat with all the material properties, weather prediction, lots of other things. But I think the heroic thing was over 10,000 simulations, I'd say complemented by data, tow tank tests, weather feeds. Okay, and the granddaddy of all of this, which was the real digital twin, was something called VPP, the Velocity Prediction Program. And it actually told you how fast this boat would sail in various conditions, upwind, downwind, what the right tactics should be. And, you know, when you look at it, a sailing course like this looks like, you know, sort of a trivial thing compared to some of the tough stuff that we do. But what you find is that the margin of victory in the race was typically 10, 15 seconds to a couple of minutes, okay? So really getting the physics right, getting the design right, ended up being a very important thing to do, okay? And, you know, as part of this story, what you find is that the boat did fairly well, but when it came down to the last race, you know, that was sort of the make it or break it moment. And Connor decided to actually make a modification, no tow tank tests, nothing of that sort, everything taken from this digital twin, which was the prediction model, okay? And it was a fundamental modification to the winglets on the keel of the boat, okay? And, you know, he won the last race, and by the way, not by a very great margin, okay? So you sort of get your appetite whetted with this. I've sort of stuck with this stuff, so here's a little bit of history. That looked like a very conventional boat. What I'm showing you here is the first America's Cup boat, 1851. 2013, when it was held in San Francisco, an incredible catamaran sailing on these knife edges that you can probably see in front of you, and an aerodynamic foil that involved a lot of invention, everything built of new composite materials. And I can tell you the amount of effort that went into computing, modeling, prediction on this took an incredibly deep pocketbook. Most of this was financed by Ellison. And in fact, I would say he actually managed to win in the end because he had that pocketbook to make modifications as things went along, essentially. And then this March, in Auckland, New Zealand, that's Prada. Again, absolutely futuristic looking, and I would say all because of the power of computing that we have today and our ability to actually make good predictions. Uh, what I would say is not all things always go well. The winner of the race in San Francisco, for example, was Oracle, but they were down 6 races, okay, and managed to win all 6 at the end, okay, by making those modifications, understanding how to manage their craft in all kinds of conditions. And if you look at the picture at the top left, you see that very slender blade. Okay, that's what the boat was sailing on. There are 4 of those, usually 2 are out of the water. So you are actually sailing on 2 very, very thin blades like that, okay? And it actually shows you one of the uses of digital twins for innovation, for exploring design, things of that sort. If you didn't have this kind of horsepower, you would never be able to do it. So let me go from that little episode to, what is it that digital twins are about, okay? And in writing this book, we have probably come right now across something like 200 different definitions. So there isn't a standard one. It's a term that people identify with. And for me, what's important about it is the following. It's a set of tools that allows you to capture the past, to understand where you are in the present, and a way of predicting the future for objects, systems, all kinds of things, okay? If you want to be a little bit more, I would say, technical about it, it's a dynamic digital representation of an asset or a physical object. I'm not going to go and read this. When you get a copy of the deck, I think you can peruse it. A little bit more complicated definition, but these are just a few of the hundreds that are out there. So, when you look at it and try to boil things down, what you can find is in today's world, people are using digital twins in many different settings. They deliver value. They help with a lot of things. They're a key in manufacturing if you're interested in Industry 4.0. They're very important if you're making products and goods. They're just as applicable to services because you can also model and create twins of abstract concepts, and really fantastic at dealing with things like processes and understanding them. So what I'm going to do is sort of take you through a little bit of a background. What I'm trying to represent in this illustration on the left, you have a set of gears. That's my real world object. It's part of a watch. And I can model it and create a digital twin of that particular watch, okay? So that's one thing you can do with digital twins. You can also build what I'm going to call virtual digital twins, to which there is actually no corresponding real object, okay? Flights of fancy of various kinds, but again, very, very important. The world is a little bit more complicated because what really makes a digital twin different from just modeling, different from many things that we did in the past, you now have a closed feedback loop between the digital twin itself and the physical object. Just like in that little illustration that I showed you with the America's Cup, okay, while the model existed, the model influenced what one did to the actual boat. One actually changed the design of the keel and the winglets, absolutely crucial to winning it, okay? That feedback goes on all the time. So what a digital twin has behind it is an incredible amount of supporting infrastructure. It's a history of data that's been collected, it's analysis tools, results of tests, resources for storage, computing, things of that sort, control systems, reporting systems, because there's a human aspect to this, and then lastly, connectivity, okay? And I can tell you a world of 20, 30 years ago, we were dreaming about these things. Today, you have the communication infrastructure. It could be from space, it could be from the ground, but that infrastructure makes all of this possible. The other thing that's crucial, okay, now is that you are motivated to put sensors and instrumentation into the design of the physical object or artifact, understand its context, collect data from its environment. Okay, so people who do products, who manufacture things, are actually for the first time actually learning how the goods they manufacture are really used on a day-to-day basis. Okay, and that informs you about what you should and shouldn't do. So when you look under the skin of a digital twin, and I'm only doing a piece of it, the first thing is, how do you actually represent it? What are the techniques and technologies behind that? How do you interface with it? How do you put the models in simulations, whether they're based on physics equations, whether they're based on AI algorithms? How do you curate the data, take the data feeds, and if you want anything of value, testing and validation is always there. And how do you do the execution so this twin can be operational or co-operational with its counterpart, essentially? Okay. If you actually start looking at more complex objects, what you find is each one of those may have a component for which you actually have a digital twin. So the problem is a little bit harder because you want to figure out, hey, how do these things work in concert with each other in a way that can actually replicate that more complex object? Okay. And then when you look at a system of objects, so I'm looking at something like a car, you have a body, you have an engine, you have brakes, you have a steering system, dashboards, a transmission system. All of a sudden, what you find yourself is a constellation of digital twins working in concert. Again, an even larger problem that's in front of you. Okay. So when you look at the world of digital twins, it can go from something very simple, I would say, to something that's very, very complex. In terms of an engineering view of it, a lot of the literature that's written takes a life cycle view. You start with requirements. I call this sort of the lust to dust cycle, go through design, development, deployment, all the way through retirement. And a digital twin actually ends up being an incredible communication device that allows you to incorporate some of these downstream stages into the early thinking that you have to do. You may start off with a digital twin that's got some properties, but you continue to build it up over time, depending on what it is that you have to retire. I'll give you an example like nuclear reactors. Awful lot of expense that happens at the very last end of the cycle. Okay, so that's an important concept. The next thing is, if you look at digital twins from being very simple to being very complex, within an organization, they can also be used at different levels of practice, essentially. Little standalone things, little better than models because they have those feedback loops in them, all the way through what I would call a level 5, where you're seeking a high level of autonomy. The DTs are everyday part of the ecosystem. Your staff and people are trained to use them. You have high fidelity and granularity in the models. You have some trust in them. You possess the infrastructure that can support them. And fundamentally, you can actually build this into a business at the same time. Okay? So that's another view, quite important. So if you look at this historically, and I see we have Krishna Patipati on today's call. He's one of the co-authors of the book that we're writing. And in fact, I took this from his and Ken Rosen's chapter. Okay, you know, that history starts in the 1970s, where engineers had ink and mylar. wooden drawing boards, slide rules, things of that sort. If you were in a big enough outfit, you may have had a mainframe computer that took up rooms and rooms of space. And the engineering design was based on divide and conquer, everything in silos, and the silos had a hard part communicating. Late 70s, early 80s, workstations, CAD/CAM comes into being. We still have room-sized computers, start the IT transformation, and I would say the invention of concurrent engineering, where you're starting to look at some of the downstream effects and in your engineering processes. Improvement in workstations, eventually sort of the growth of the kind of computing that we have today. So an improvement every 18 months to 2 years in terms of what we can do. So there are two fundamental things that are important to the digital twin. I don't think they would exist without that continued growth in computational capability. And they also wouldn't exist without the creation of fairly powerful enterprise-wide tools and processes that can actually exploit that kind of horsepower. Okay. So if you then take a look at it, what you find is, and I think I mentioned it previously, the underlying representation of what you do in a digital twin is critical. It can be for things that are visual display of information. Human beings make most of the calls. It can be data-driven. It can be based on logical relationships, domain-specific physical models for which you better have all of the data and techniques, things that may be event-driven as opposed to just purely time-driven, things that are knowledge-driven, and then things that capture experience, okay? So those are all important aspects to keep in mind. If you then look at it a little bit more closely, there's an awful lot of pretty stuff. I used to call CFD colorful fluid dynamics. In digital twins, people make very nice 3D objects full of color, all of that. That's all very nice. It's useful for some things. But I can tell you the collection of data, putting it through an AI algorithm, even feeding something like a weather system for that, let's say, sailing example, process-oriented, model-oriented, very different world if you're dealing with services and want to replicate the kind of things, let's say, a financial institution or a bank is doing, or things that are logic-oriented where the relationships between things actually dominate, okay? And I can tell you, it touches almost every aspect of computer science when you try to go down this thing. So let's take a little bit of a look at the technologies that are involved. Very similar to what you find in the Internet of Things. Very definitely computing. I need storage. I need connectivity, because that digital twin could be totally distributed from a piece sitting on an object all the way to somewhere in the cloud. You want to be able to deal with that. Sensors of various kinds, actuators. I need to put human beings in the loops. I need to have an interface with it. Very difficult things in terms of dealing with the software suite, everything from operating systems to the way you actually put those together. And then you quickly discover everything needs power and energy. If you start looking at the building blocks, again, I would say that life cycle view makes a lot of sense, okay? But the first thing I'd like to say is when you start practicing that and going to look at a specific application, it really helps to understand the domain knowledge. Sometimes we have new techniques. The people who actually understand their own area, the markets, the nuances, all of that are just as important. It ends up being one of the roadblocks in the way we sometimes sell things. and I'll come to that in a minute, okay? But this is important. The other one is all kinds of ancillary technologies. Again, domain knowledge is key. It's hard to get anywhere without doing that. But it's things like, I see I have a little scanner in the transom, photogrammetry, one of the easiest techniques for getting hold of data. I don't care whether it's satellite data that McDonald Detweiler put together to create synthetic apertures, whether it's stuff from drones, from the ground. It's a way of capturing the world and the stuff around it. All of the things in data science, today, additive manufacturing, which again puts a premium on these things. The world of modeling, I actually call it muddling, meddling, and modeling, because we don't always do this well. Augmented reality, every form of AI you can think of. Again, sort of AI, computational geometry, and stuff like the Internet of Things. All of those technologies tend to play at various levels in this game. So let's take a look at sort of the business value of this. And the first part is, why do you put these twins together? One is to make predictions, to help you make decisions, and to have effects. Okay? And so when I look at the fundamental value, there's a whole bunch of this, which I would say revolves about making things more efficient, conquering the complexity that we have, so we don't have to just divide and conquer, but sort of consider things as a whole, implementation of various forms of optimization, redesign and refactoring, okay? Big push towards automation. It's all across manufacturing, but I would say all kinds of other areas. Very definitely innovation. It allows you to do the what ifs that you couldn't otherwise. Whoops, need to go back. For many outfits, it's really sort of existential, okay? If I think of, let's say, Boeing with all of its troubles recently, the ability to actually put the company's fortune at stake by building a new plane, an absolutely essential tool used the right way. So it helps you make good decisions, helps you avoid making bad ones. Lots and lots of uses for avoiding risk and, for risks, hazards, assuring safety, the management of assets of all kinds of classes, and then very, very important, I would say, creating new user experiences. As part of this book, I have one co-author, Larry Schmidt from the Innova Group. He's taken a look at roughly 50 business models. There are 5 that stand out: being an aggregator, fractionalizing, collecting data from stuff, providing a twin as a service, creating a multi-sided market platform where people who need the kind of information that goes into this pay for it, and so does the end user in a way that's fair and well balanced. And then I would say the standard razors and razor blades model. Okay, so I wasn't going to spend a lot of time on it, but Larry actually had a very, I would say, inspirational thought, because when you look at the way we started thinking of digital twins, it was to build stuff around the physical object. Okay, I'd say the reality of what we are seeing is that it is actually the physical that's the twin of the digital object itself. Okay, and I think we seem to be going more and more in this direction, because once you have invested the time, put all of the knowledge systems together, captured in something like a twin, okay, the ability to go through, reuse it, change the materials, change the design, okay, it really brings you up considerably in the way you can do that. So a lot of intellectual property and know-how really ends up being embedded in what the twins do for you. So let me, look at values sort of in general, and this would be in a, I'd say, societal sense. One can have value for businesses. One can have value for government by actually understanding what we do. If I were to look at our health system and try to build a digital twin of what goes on in that health system, trying to cure its ills, for example. I have seen a lot of people try to do this kind of models for the pandemic, try to go through the whole cycle. Very, very complex to do. So the example I'm going to show you was actually done for Notre Dame. You see the cathedral there before the fire. And what you see there is a laser scanner. And as luck would have it, a few years before the fire, somebody thought of taking Notre Dame and actually digitizing and building a virtual model of everything that's there. I think the lower left hand shows you the locations of where those lasers were placed for scanning. When you do it with multiple lasers from many, many different directions, you can actually uncover what the geometric object is. But you can also learn a tremendous amount of information if you're using multicolored lasers, a lot of stuff that the eye cannot actually see. You will see flaws, you'll see cracks, you'll see condition problems, okay? So all of that, it turns out, was actually captured. Okay? And the consequences, even before the fire, because the fire happened during a renovation of the cathedral, there was a very complex set of physical digital twins that was actually put together, okay? And again, I would say Larry's contention was that these have a life well beyond, I would say, the life of the actual physical object. I can say, somewhere in my career, when I was at SAIC, I had a group that did a lot of structural engineering and structural analysis. They built a tremendous model of Capitol Hill, roughly 350 million nodes. I think that was Yossi Baum and Reinhold Lohner. And I can tell you to this day, that model gets a tremendous amount of use because it informs you about things other people don't quite understand. Okay, and so in the end, for rebuilding the cathedral, the twin serves as a template. Okay, but now what you have the challenge is, how do I now use that template to put in new methods of construction, new materials, things of that sort, along with all the analysis tools I have for knowing how this structure will perform structurally under various conditions and in the kind of environment that it lives in. Okay, so let me at this point turn and talk a little bit about applications. When I work at IEEE, people think of me as somebody who does telecommunications, things of that sort, and IoT. So I'm going to take you to a very different world. Again, an experience from the past. We had a very large program jointly with the shipbuilders, naval shipbuilders in the US, Lockheed Martin, quite a few people out west, Dassault Systems, UGS at that point, they still weren't part of Siemens. And here's what we looked at. How can you improve engineering in some fundamental way? So the program was called Simulation-Based Design. And we took a look at a lot of objects. If you look at the one on the left, it's an aircraft carrier. It has roughly 1 billion parts plus, and around 35 million discrete components, okay? If you take a look at an aircraft, what you're seeing is a 777. That has around 3 million parts. The bigger jumbo 787 run up to roughly 7 million, okay? A car, by comparison, fairly simple, 20 to 30,000 parts, including all the screws and rivets that you're going to put into it, okay? So for this program to understand scalability, what we ended up working on is, well, the biggest thing you can work on, which is aircraft carriers. So the example I'm going to do is talk about shipbuilding, large shipbuilding, and the progression of things over time. So in this view graph on the left-hand side, that's the drafting room. It happens to be, the drafting room was in Belfast. And this is the way the Titanic was designed, okay? Big sheets, everything on vellum and paper with ink. I can tell you most places maintained that tradition well into the 1970s, okay? Little drafting table up there. And the way you figured out whether you did stuff right or wrong is you had a carpentry shop, you build models, you looked at your arrangements, you figure out what would interfere with what. You didn't have anything inside a computer in those days, okay? And again, that persisted for an amazingly long time. If you fast forward to today and look at something like an aircraft carrier, almost all of it is in CAD/CAM drawings at this point. All the geometry is captured. Everything is done on workstations, all the complexity, and a lot, I would say, of bits and pieces that are specialty items, pre-designed, pre-canned for reuse, essentially, okay? You know, just to give you a feeling for it, a carrier takes roughly 7 to 8 years to build. Cost is amazing. If I look at today's carriers, they're built like no other ships in the world, okay? So let me go a little bit deeper, okay? So if you were to take a look at a shipyard, this is Newport News. It runs roughly a mile along the James River. This is where they build two things. They build submarines and they build aircraft carriers. You know, if I look at the way this place used to operate, they used to have their own bricks that they made, their own carpentry shop, their own woods from which they got it. It was a totally vertically integrated organization, okay? If you look at the building on the right-hand side, that's the engineering building. It's got all the workstations, the engineering crews are all there, and they can pipe information all the way down to the manufacturing floor. And as I showed you some of the technologies, the gentleman down at the bottom right is working on a pipe bending machine, okay? And he gets his instructions actually from a laser running down, up and down the ship that's already been built. So the pipe comes in and joins perfectly within tolerance of you know, exactly the number of bends it needs to have in it, the lengths it needs to have. All of that is integrated. What is interesting is if I look at this one building, it's roughly 1/10 the volume of what it took to actually store all the drawings for the carrier, okay, when they were drawn on paper, okay? That was actually an amazing facility just by itself. And being able to do all of this virtually and have those digital twins makes all the difference in the world. The next part is you see the ship actually under construction. And the way this now works is you have huge cranes, okay, that move sections. Those sections in turn are actually built in front of machines where the worker is in an upright position, okay? unlike what used to happen in the past, that you used to lay the keel, put up the hull, and all the welding, all the fittings, all of that kind of stuff used to be done by people working in very, very awkward positions, okay? And so here you buy yourself the biggest crane, you figure out how to make small parts, assemble them into big parts, and then you plunk those big parts and assemble this very much like a set of Legos almost, okay? Again, if it wasn't for this digital technology, the photogrammetry that's involved, none of this would be possible, okay? So there is another trend in all of this, okay, because what you're doing is building components, manufacturing them, and then assembling them. Newport News used to actually have different plants for the way it did submarines versus how it did the parts for the carriers. What they have done is done a joint manufacturing facility, amazingly flexible. Everything, every piece of information arrives digitally. Your scheduling, everything of that sort. So in some sense, there's actually a master digital twin of the yard and the way it functions. Okay, so this is a good example of its use. I'm going to go back a little bit to that first example that I showed you, which was the America's Cup, because one of the people working on it was Neil Salveson. And what he contributed from the naval architecture point of view is, how do you model the ship? How do you understand how it'll react in real seas? Okay. If you look at what used to be the standard, you did a static analysis. You put in a safety factor, and all of the rating companies that would eventually result in issuance of insurance to the shippers would use those to rate the ships and set the insurance rates. Niels was actually given a puzzle, okay, and that is there's a class of ships of which 3 had disappeared without a trace. Okay, and he had done some very nice work, having access, I think, to the largest cray at the time, not only to do a static analysis of how the ship reacts, but to actually do a dynamic analysis. And what he discovered is that whenever the bow of the ship came out of the water and it slapped down, okay, called a slapping event essentially, and a slapping load on the ship, it worked the ship like you would work or twist a pin, a paper clip or a pin essentially, okay? That paper clip, if you bend it back and forth, will eventually break. It's crack propagation, okay? What Niels discovered is by doing these calculations, creating a very high fidelity model of the ships he was looking at, is that all that bending would make a large section, it was a section almost 20 feet on a side, that would suddenly fall off the ship and it would sink, okay? And the ability to have this level of calculation, be able to build twins of this sort, actually allowed him to solve the mystery. Okay, I'm going to change pace altogether at this point and give you another example and say the following. If you look at where digital twins probably have the most maturity, it's actually in doing manufacturing. I have on purpose sort of stayed away from that because you can find a lot of material on it, and just trying to make the point that it has utility in all kinds of other settings, okay? So this particular adventure starts off with a real tragedy. There are 9 blue whales in the Gulf, at the mouth of the Gulf of the St. Lawrence, who got trapped in the waters in high numbers and perished, all 9 of them essentially. I got a call from a friend who's Canadian, lives in Toronto, Gordon Eberts. And Gordon said, boy, you know, we need to do something about this. And he contacted the Royal Ontario Museum. What we actually organized is a way to process two of those whales, okay? And you may start asking yourself, what the hell does this have to do with the digital twin? So I think we'll come to that in a second. So this is what one of those whales looks like, roughly 50,000 pounds, okay? It gets cut up, it gets processed. The process takes roughly a year. They put them into these TU containers with horse dung. And this is to get rid of the flesh and get rid of the oils from the whale, so you can eventually end up with the bones. Okay, after it's been processed, you go through and mount the whale bones. Again, very tedious, very expensive thing to do. So you end up with the model. Okay, and then at the very end, this whole structure is actually scanned. Okay, it's very high precision laser scanning to actually build a digital twin for this particular whale. Okay, if you start taking a look at international rules, it turns out the export or import of whale bones is forbidden. And there were a few people who had asked the Royal Ontario Museum whether they could actually have a whale for their exhibit. Okay, the answer is very hard to get. So what happens in the end is you actually create the digital image, and it allows you to do a number of magic things. First of all, you can scale the skeleton up and down, and using additive manufacturing techniques, actually print a new whale for yourself. Okay, you can print it as a small toy. You can print it for somebody who wants to have it outside of the appropriate materials. You can do stuff that's important for the science involved, for people who study the physiology of whales and things of that sort. Really another use of this technology, I'd say for preservation. But as you'll find in this presentation, if you're interested in it, I have a fairly extensive bibliography, because this is just as important for cultural heritage and things of that sort. We're being able to understand objects in depth, what materials they're composed of, what they look like, what colors they have on them. All of that is important to us as part of our culture. So I'm going to spend the last few minutes just whizzing through the kind of applications that you find, and again, trying to stay away from manufacturing. A lot of stuff in the health sciences, healthcare, medical models, diagnostics, personal health, incredible amount of use in athletics, both for personal health and for training. Okay, and what you'll find is startups in the hundreds in these areas at this point in time. Okay, a lot of them in the valley, but elsewhere in the world at the same time. If you look at the oil and gas industry, the stuff on the left, you know, a typical platform in what I'd say, you know, the deep Gulf, North Sea, any of those kind of places, there are two things, exploration and production. Again, digital twins all over the place at this point, very complex structures. It's hard to actually deal with them and know what you're doing without having everything digitized for you in a form that also talks to the models, not only of the platform itself, a model of the oil field, things that allow you automation, ability to deal with the weather, the hydrodynamics of the platform that you have out there. Again, really multidisciplinary and exciting stuff. The one on the right, by the way, was wind power, things of that sort. That whole industry is all over this, everything from preventive maintenance to design to dealing with problems like, why did all my blades delaminate in the last storm? So, okay. So I think with that, I'd like to thank you and take a few questions. What I do have is this fairly extensive bibliography at the end, and I think Dejan will make the deck available to all of you. Okay, so thank you.
Thank you, Adam. I knew you were a great speaker, but this has surpassed any of my expectations. Really excellent, insightful, and I can keep on and on. But in the interest of time, let me read some of the questions. And I think the questions are as good as your talk. Greetings. Does the alphabet, in parentheses, encoded for computing purposes, by default map to a digital twin? Dr. TV Gopal.
Does the alphabet map to the digital twin?
Yeah.
Tongue in cheek, I'm going to say, if it doesn't, one can make it do. Okay.
Dr. Gopal, did you want to comment on this some more, or?
Yes, thank you very much. The concern here is that our quest is to make the digital twin tend to the reality as much as possible. It can start with the keyboard. Whatever is punched into the keyboard as a character, makes sense.
No, let me actually put it this way. It's an interesting point of view, but a lot of what goes into the digital twin does not come from the keyboard. Okay, and the next thing is, when you say it conforms to reality, the reason I actually put up a virtual digital twin is it can also conform to your fantasy. What goes on in your mind, okay, may not have a physical object associated with it. Okay.
Thank you.
And yeah, I'll tell you a good example was the following. You have that fantastic statue of Michelangelo in Florence. Okay. Well, the guy who built that saw a piece of marble, and somewhere in his head he imagined what that piece of marble could turn into. Okay. So I have a whole bunch of authors actually working on what I call digital twins for the arts. Okay. And what you're able to do in that virtual world is actually replicate the process by which that piece of marble turned into that marvelous statue. That's one part. Then there is a whole bunch of new art, okay, which is all being created digitally. And it's pleasant to see, okay? And there was no corresponding physical object, okay? So I'm not quite sure I want to do this from a keyboard. I'd rather tap your brain for it.
Thank you very much. It's a very nice lecture. Thanks.
Okay, thanks for the question.
I think therefore I am. Thank you.
Yeah. Okay, so the next question is, in digital twin definition, you mentioned how the defining characteristics of a DT is the closed feedback and feed forward loop between the physical twin and the digital twin. Could you elaborate on what type of actions in the feed forward and feedback are typically considered as essential parts of the digital twin? For example, is root cause analysis of vulnerability in a system be considered an action?
Well, so let's put it this way. I would say finding the root cause is not the action itself. It's only if you actually build the next layer of analysis in there, which says, here is the root cause, okay, but here is also the prescription of what I should do about it, okay, and the digital twin in some ways has the control system built into it that launches that action. Okay.
Okay.
Okay, so that's one. But for all of that to work, I have to collect enough data from the real situation or the real object, okay, that I have a level of confidence that the fidelity and granularity is good enough. And like I would in a mechanical system, so I have a governor that I can't make, I would say, decisions out of bounds. Okay. And this can lead to a whole discussion about AI, what it does and what it doesn't do today. Okay.
Yeah. And it's excellent segue for my own question. There's a lot of discussion about ethics in AI.
Yeah.
So how does relationship of digital versus physical twin map in that ethics in AI, or digital twin to another digital twin?
So let's put it this way. Let's say I am actually putting together a digital twin that's built around process. Okay. And the process is in the financial sector of who do I make a loan to and who do I not make a loan to. Okay. If my digital twin ends up governing those actions, it sort of inherits, I would say, the prejudices that are built into the algorithms. Okay. So figuring out how to guard against that is as much a debate in this particular realm as anything else. Next thing is you have safety factors. If you're using it as a control system, and the question is, do I let the plant go down or do I harm a human being? What decision do I make? Okay. Yeah. I would say all of those kind of discussions happen in this space also.
Okay. The next question, can you please expand to a next level of detail, abstraction, on the 5 business models further, aggregator, etc.?
Okay. So let me give you, I'd say, a couple of examples. Let's start off with the aggregator. I don't know how much we'll go into the others, but you know, easiest example, and in fact, we have a chapter coming in on this. If you look at it in the US, we have a nuclear industry where we had commissioned 104 plants. Okay, number has gone down over time. Those plants have components from vendors all over the world, essentially. They're pumps, they're valves, all kinds of components. Okay, and an aggregator would actually take the data and protect the data from all the operators, okay, of any piece of equipment that may be failing, has a problem, okay? And on the basis of that, you start making decisions, okay? You know, what's causing all the problems? What's causing all the risks, okay? An aggregator knows that. I can do that with cars. I can do it with almost anything else that's out there, okay? Okay, and the framework for doing this, okay, is a digital twin that ingests that data, analyzes it in an appropriate way, okay, and then allocates that as root causes to the right places, okay. And now, you know, for the greater good of an industry, they become very, very important in the way things are done, okay. So that's an aggregator, okay. I would say if I take a look at something like that razor blades model, you know, I happen to have a watering system in my backyard, okay, and I noticed that the outfit that provides me with that, okay, has improved what they do over time, and they improve it this way. They get the weather feeds. Okay, when they get the weather feeds, on the basis of that, they decide, hey, I am not going to water the lawn today because it's rained. Okay. They also have a few sensors in the ground say, well, it's not raining, but the soil is already moist enough, okay, therefore don't do it. Okay. eventually what I see them doing is actually creating a little digital twin of my backyard, okay, that not only controls whether I water or not sort of wholesale, okay, but whether I put enough water in the right place. So if you look at the agricultural folks, they're doing that left and right now. Okay. And so what you can think of it is it's sort of a water jet printer that prints where it's important and where it's not. Okay.
Okay, Adam, I think we're 7:02. I'd prefer to be on time, respectful of
Thank you.
our audience. I highly appreciate and thanks the whole audience. It was amazing, exceptional talk. Once you have exited, as you know, it will save in your local drive somewhere, and then if you can send it to me together with a presentation.
I will do that. Okay.
Nice.
Thank
Thanks
you.
again.
And thank you all for listening. Really enjoyed this. Okay.
Okay, bye, Adam.
Bye-bye.